Yeah, so thanks. So this is some joint work I've been doing with two of my former master students, Briët and Umberto Tarantino. There are different ways to explain arrow algebras, but the way I will try to motivate and explain them in this talk is as a generalization of locales, where we want to generalize the notion of locale to include also structures that have more of a computability flavor. So what is a locale? Well, they've been mentioned before at this conference. So a locale is a standard way of trying to do topology in a constructive context. So they're also called point-free spaces. So a frame or a locale is a poset that has finite meets and arbitrary joins, with the infinite joins distributing over the finite meets. And an important class of examples of these things are just a collection of opens of a topological space. And that also motivates the definition of a morphism of these things. So a morphism between two frames or locales is a monotone function. So if in the frame direction we go, it's a monotone function from L to M, which preserves these finite meets and arbitrary joins. The category of locales is defined to be the opposite of the category of frames. So that because in that we do that, then actually this functor, which takes the opens of a topological space, becomes a functor in the covariant direction. So yeah, this functor is not an equivalence, but if we restrict it suitably, it becomes an equivalence. So one aspect which is interesting about locales is that once we have a locale, we can construct a topos out of it. There are different ways of doing this, but one way is doing this via triposes. So we take the locale, we construct the tripos, and then we do something called the tripos to topos construction. So the triposes were also already mentioned before at this conference. So for me, triposes live over sets. So I have a pseudo-functor from sets. And then to every set, it assigns a pre-Heiting algebra. So it's not a Heiting algebra, but it is a pre-order version of a Heiting algebra. And we think of the elements of P of X as the predicates on X. So we the fact that these are pre-Heiting algebras means that we have an interpretation of propositional logic. Then for every function, f from y to x, we want an operation from p of x or p of y, basically substitution. And then we also want the quantifiers, that those are the adjoints to this substitution operation. And then we also have an axiom basically saying that we have an impredicative type of propositions. So that says that every proposition A in P of X can be obtained as a pullback or a reindexing of one very specific one. So these things you should think of as models, as a version of higher order intuitionistic logic with an impredicative and also an intentional type of propositions, because this map A, do you have a pointer or something? No, the pointer is gone. This map A over here is not required to be unique. So how do we construct a tripos out of a locale? Well, we can just say that the predicates on a set X are just functions from X to the locale. We need to order these, and we just take the pointwise ordering, and then you can check that all the conditions are satisfied. And then, as I said, I mean, once you have such a tripos, you can construct a topos out of it. It's a very sort of setoids-like construction. In some sense, you make the whole model, in a way, extensional. So the objects of the topos become some pairs, partial equivalence relations, also mentioned in the previous talk, and then functional relations between them. Now, the thing is that, great, thank you. Was that a pointer? Yeah, but I can't switch. Okay, okay. Not yet. Okay, so why generalize? Why generalize locales? Well, there are many interesting triposes that don't come from locales, that are non-localic, So one important example is the effective TYPES. So then we take on a set X as predicate functions from X to the power set of the natural numbers, the realizers, for that, the fact that it's X has some property. And then if we have two such predicates, we will say that one implies the other. If there's a partial recursive function that for any X and any realizer of phi of X computes something which is actually a realizer of psi of X. That also satisfies the axioms for TYPES, but is not localic. And so you might wonder, is there kind of a natural generalization or some generalization of the notion of a locale that would also cover examples like the effective TYPES, some sort of generalized locale, and hopefully we can also then construct toposes out of these as some sort of like sheaves over generalized locales. So that is the problem in some sense that arrow algebras solve. So, so first we start with a complete poset with some sort of order on it. And then a binary operation, which we call implication, which is monotone in the second and antitone in the first component. So every locale is actually a complete Heiting algebra. And actually the formula for the implication is just this. And also, as another example, we can look at the power set of natural numbers ordered by inclusion, and then we have this sort of Kleene implication. So if X and Y are sets of natural numbers, then we can look at a set of natural numbers E that are codes of some sort of partial recursive function that whenever you give it an element in X is defined and belongs to Y. So, I mean, there's this ordering. I will call it evidential ordering, or maybe you should think of it as a subtyping ordering. And the elements of this arrow structure you could think of as pieces of evidence or truth values. But it's important that actually there was going to be another ordering on these things, which I will call the logical ordering. So in some sense, this one is somewhat auxiliary concept. So what is missing from the definition of an arrow algebra? So it is going to be an arrow structure, and then we should also tell which truth values, which elements, pieces of evidence we consider conclusive. And this is these are sort of those which belong to a certain set S, which we call separator. So what are the axioms for a separator, the true truth values? Well, they should be upwards closed, they should be closed on the modus ponens, and they should contain certain tautologies or combinators. And okay, these K and S, I think, are the well-known ones from, I don't know, Hilbert-style axiomatization of intuitionistic propositional logic. And then there's this mysterious additional combinator, which I call A, which I'm not going to explain, but I think it's the one that makes the theory work. Well, important parts of the theory. Yeah, and then an arrow algebra is just such an arrow structure together with such a separator. So any frame is an arrow algebra where we should just take as a separator just top. Actually, when in the setting of a frame, such a separator is actually the same thing as, or locale, such a separator is actually the same thing as a filter. So every time you see a locale, you can put and a filter, you can take the pair of those two things and it will become an arrow algebra. And to fake you could also look at the effective arrow algebra, then you also have to say which sets of realizers you consider true, and those are the ones that are actually inhabited, contain at least one element. So I claim that from any arrow algebra you can construct a TYPES. Let me first explain how you construct from any arrow algebra a pre-Heiting algebra. So if you give me two elements in the arrow algebra, I will say that A entails B if the implication belongs to the separator. So if the separator believes that A implies B is true, and then you can easily check that this satisfies, well, no, actually you need to know a bit of combinatorial logic / lambda calculus, I think. But okay, so if you do this, then you can check that this is a pre-Heyting algebra in which the implication is actually just given by this symbol. And this in some sense is the most important ordering, which I will call it the logical ordering. So this is how I get a single pre-Heyting algebra out of an arrow algebra. So actually I want to have one for every set, right? So how do I do that? Well, if you give me an arrow algebra like this and X is some set, then I can look at all the functions from X to this arrow algebra, and I can just take the implication and the order to be pointwise. And then I need to choose a certain separator on this set of functions. And there are two choices, and I take the sort of the uniform choice. So I will say that a function x to a belongs to the separator if the big meet actually belongs to the separator. So there's, in some sense, there's one element in the separator which is below every phi of x, instead of, which is much stronger than saying that every phi of x should belong to the separator. Yeah, and so if then I have the family of all of these pre-Heyting algebras, if I take if I order them like this, and that gives me a triples. And in this way, I recover both localic triples and the effective triples. Okay, so I mean, I gave you the effective triples as one example, but actually we have a whole host of examples. Basically, every PCA gives me an example of an arrow algebra. So what is a PCA? Part model. So it's basically a model of combinatorial logic. So you can see here there's a K and there's an S satisfying KAB equals A and SABC equals ACBC. But we can weaken this in many ways. First of all, we can make the application partial. Then we have to still assume that the domain of application is downwards closed. We can turn it into a poset and then only require these axioms up to an inequality. Then we can also choose to say that the real realizers are those which belong to a certain set A hash, closed on the application, containing the two combinators K and S, and also being upwards closed. So I mean, there are many ways of sort of still getting a kind of structure, which is a, yeah, I mean, this is not the standard definition of a PCA, but it's a very general concept in which we can fit many examples. So here I have a few. So so we can take K1, so that is the set of natural numbers with application, just clean the application. If we want to have an example where this an ordered example, we can look at terms in the untyped lambda calculus and read this as multi-step beta reduction. We can also look at, for example, Scott's graph model, which is a model of the untyped lambda calculus. And then we can choose this nice, so that the elements there are a subset of the natural numbers. And then we can look at this P, we choose P hash to be those things which are computable in the sense of being recursively enumerable. So then you can sort of see all the different features. So this one is partial. Anyway, this one is ordered, and this one has an interesting filter. So, and when in this setting, we can look at the collection of downwards closed subsets. Ordered by inclusion, we can take this kind of clean application again and choose as a separator those downsets that actually contain an element from the filter. Okay, that should be A hash, I guess. We've been switching between different symbols. Yeah, anyway, which contain an element from the filter. So that gives me a notion. Also, yeah, so that also gives me an arrow algebra. The chair is still in the seat. Okay, great. So, so I think one of my personal motivations also in doing he's now no. I've waited. Okay, how much more time do I have? 6 minutes. Okay. So one of my personal motivations for this is also to have a theory for these arrow algebras which mirrors locale theory. So for example, one thing that we have in the theory of locales is we have a notion of a sublocale given by a nucleus or a local operator or Liouville topology. Also seen many times at this conference already. So this is some sort of monotone operation which satisfies these sort of monad laws. Well, there are many examples of this, but the nice thing about it is that once we have such an arrow algebra and such a local operator, we can easily construct a new arrow algebra. So we take the same set A, the same ordering, and then we redefine the implication and the separator in this way. So this is sort of like a Kleisli implication, if you want, and then the things which belong in the modified separator are those things that belong to the separator after applying J. And you can check that this satisfies the axioms of an arrow algebra. Yeah, and so if you take the arrow triples associated to this one, you get a subtriples of the one associated to A. And actually, any subtriples of this arrow triples over A is of that form. So I especially recommend the work by Tarantino, Umberto Tarantino, who has actually developed a nice notion of morphism of arrow algebras, which I think satisfies all the things that you want. So if you restrict it to locales, it's the traditional notion of locale morphism. If you restrict it to arrow algebras coming from PCAs, it gives you what are called computationally dense morphisms of PCAs. Morphisms arrow algebras correspond one-to-one between geometric morphisms between the associated triplexes, and also there's a nice factorization on this morphisms as surjections followed by ejections, which exactly mirrors the one that we have for triplexes. So I should say that everything that I've said so far is heavily inspired by the work by Alexandre Miquel on implicative algebras. So I mean, okay, this is a bit in reverse, but you could say an implicative algebra is an arrow algebra that satisfies this axiom. So actually, Miquel has two nice results showing, first of all, that every tripos over sets is isomorphic to an arrow tripos coming from an implicative algebra, which in particular every arrow algebra is equivalent in a suitable sense to an implicative algebra. So you might wonder, why not work with implicative algebras, giving these results? So I think for me, and that is also the motivation for developing this theory, is that there are many naturally occurring examples of arrow algebras that are not implicative algebras. So you can modify it using Miquel's construction, which is non-trivial to turn this into implicative algebras, but yeah, then for purposes of doing computations, I think that is not a very useful thing. And then this factorization of morphisms into surjections and inclusions, where the thing in the middle is just this simple construction, also don't think that that works for Miquel. So yeah, these are my reasons for wanting to generalize the theory, and I thank you for your attention.